In this video, I will tell you about glacial-interglacial cycles and a curious time interval known as the mid-Pleistocene transition. Earth's climate has varied significantly in the past. Over the last 2.5 million years, large ice sheets have repeatedly grown and melted in the northern hemisphere in what are known as glacial-interglacial cycles. Glacial periods describe the colder intervals of time when ice sheets extended into northern Europe and North America, whereas interglacial period correspond to times where only the Greenland ice sheet resides in the northern hemisphere. For the last 12,000 years, the Earth has resided in an interglacial period known as the Holocene. The growth and decay of these ice sheets is thought to be triggered by variations in the amount of solar radiation they receive during the summer months. These variations are driven by changes in the Earth's orbit around the Sun. During summers with weaker solar radiation at the high northern latitudes, summer temperatures become milder, enabling the large ice sheets that characterize glacial periods to form. Interglacial periods, on the other hand, tend to occur during periods of more intense solar radiation, by driving the melting of ice sheets over North America and Northern Europe. By drilling ice cores to the bottom of Antarctica, we have records on temperature and CO2 concentrations going back 800,000 years. They show that glacial-interglacial cycles have a frequency of around 100,000 years. To go further back in time, we have to rely on information contained in marine sediments at the bottom of the ocean. These records reveal a gradual transition from shorter 40,000-year cycles to the 100,000-year cycles seen in the ice core record. This transition from the 40,000 to 100,000-year cycles occurred between 1.2 and 0.9 million years ago and is known as the mid-Pleistocene transition, or MPT. With no significant changes in the cyclicity of solar radiation during this period, the answer remains unclear. Some of the hypotheses for the MPT involve a long-term cooling of the Earth driven by decreasing atmospheric CO2 concentrations. Unfortunately, we lack high-resolution records of CO2 across this key time period. For this reason, the ongoing Beyond Epica project aims to recover the oldest continuous ice core from Antarctica. By extending our ice core-based atmospheric CO2 record to 1.5 million years, it should help improve our understanding of its role in triggering the mid-Pleistocene transition. I'm part of the Deep Ice project because I'm fascinated by ice sheets and their importance for our climate.